So, I was discussing about this work by Werner and Wolf, which is the bound entangled okay. So, bound entangled Gaussian states. So, this is by Werner and Wolf PRL 2001. Okay. So, the main results of this paper are two. So, number one, that any Gaussian, any 1 cross n mode. So, that means with Alice this is the single mode, and with Bob n mode, n can be anything, okay, or the opposite one, or n cross 1. Gaussian state is separable if and only if. So, this is rho a b, okay, if and only if rho a b t a is greater than equal to 0, or t b also. I mean anyone can work. Okay. So, this is first one. Secondly, there exists a 2 cross 2 mode PPT Gaussian states, Gaussian entangled states. Okay. So, these are the two main results, okay, of this paper. Now, there is another work by, I think it is by Pavel Horodecki, I am not sure where it has been published. This is around 2002, okay. It is there in the archive. So, where they have claimed that finding out a bound entangled Gaussian state is, I mean the, let me put it in a, so you choose a Gaussian state, choose a Gaussian state, okay, of let us say n cross m mode, right, where of course I mean both of them should be, I mean both n and m should be greater than 1, right. Then and let us assume that choose let us say an entangled Gaussian state, okay, right, an entangled Gaussian state of this mode. Then the probability that, so let me call it as rho a b, probability that rho a b is bound entangled is very low. Very low means almost 0. Okay. So, if the state is entangled, this n cross m mode state, Gaussian state, then it has to be distillable most of the times, okay. Almost every time it is distillable, right. So, this is the result which I have not seen any published version of it, but this is what they are claiming, that if I go to finite dimensional system, this is not the case. Finite dimensional system, if you go beyond total dimension 6, then you can always figure out some bound entangled states, okay, even some parametric version of that. I mean, I am not talking about the volume wise. See, volume wise, of course, the volume of separable states is much lower than that of entangled state, that is true, any dimension. But this says that it is a rare event to figure out. So, which means that if I am working with Gaussian states or system of Gaussian states, then it is good for that, because it is most of the times it will not be bound entangled. So, therefore, you can distill and use, it will be useful. Okay. So, let us go back to this work and see how do they prove this thing, and this is just an example. Okay. This is actually not just one example, although they have given one example, but using symmetry you can create plenty of other examples. Yes, yes.
It's 2 cross 2. So.
Yeah, but even that it is quite rare. The examples that you will get, it is not a continuous family. Yes, yes, some discrete cases most of the times. Okay.
So when they talk about this quantity, they are like sampling from some random set of
Exactly. Yes. I mean, of course, the state has to be Gaussian, that is for sure.
But with that constraint, they will construct some
randomly selected states, and then they can figure out that yes. So, it is a rare event basically, which, as I said, which is good for us. Okay, good. So, there are some notations that we need to use. So, let us say that the null space of this is the covariance matrix plus iota by 2 omega, right. We know that if this is a valid covariance matrix, then this is greater than or equal to 0, right. Okay. So, null space of this. So, what does it mean? It means that this is n. So, this is the, let us say this is a maybe n mode system. Total number of modes is n, capital N, right. So, this null space of this is the set of vectors phi, right. If you want, you can call it a vector, and these are vectors from where? This is what is the size of this? This is 2n by 2n, right. And yes. So, therefore, this is an element of C to the power 2n such that gamma plus I by 2 omega acting on phi gives you 0. So, this is the null space. Okay. Right. And similarly, so when I apply this partial transposition rho a b, so the total number of modes in A and B is capital N. So, like you can say A is small n mode system and cap B is small m mode system. So, in other words capital N is equal to n plus m, right. Okay. So, if I look at the Wigner function of let us say rho A B T A for example. So, we know that this is, so let us say this is at a point R T, where this R again this is a phase space point and now the phase space is 2 n plus m, right. This is my phase space. So, this is W rho A B and now here it should be lambda R transpose. And what is lambda? So, lambda, you see this lambda is diagonal of so because on A system I am doing this thing. So, the position it will not change, momentum will get a mirror reflection, again position momentum 1 minus 1. So, this is your 2 n mode and then again 1 1 1 1 1 1, this is 2 m mode, right. Is that clear? This is how we get the partial transposition. So, we have discussed for 1 plus 1 mode just only 1 minus 1 will be there, but in this case because we are doing this partial transposition on A subsystem, this is what you will have, right. Is that okay? This is basically the effect of partial transposition at the level of Wigner function. So, here if rho A B T A is also greater than equal to 0, that means rho A B is having PPT, right. So, which means E is PPT. Then, so this is basically, so if this is the case, then the corresponding gamma matrix, I mean the covariance matrix T A A B, this should also satisfy I by 2 omega greater than equal to 0. Do you agree? Because this is a density matrix in that case, right. So, then it has to be satisfied and this is equivalent to that we have seen for the 1 plus 1 mode case. This is gamma, the original covariance matrix of rho basically, plus I by 2 omega tilde greater than equal to 0, where this omega tilde is lambda omega lambda, right. This is what you will have. Okay. So, if I now look at the null space, which is set of all vectors, let me call tilde vector, I mean just for to have different notations. So, gamma plus I by 2 omega tilde acting on phi tilde is equal to 0, right. So, this is null space. Of course, I am assuming that this is the case. Is that clear? Right, and these null spaces will be useful for us. In fact, what we can prove is that, so this is what you can prove. I am not going to prove it, but in principle this can be proved, it is not needed. So, rho A B, okay, so actually no, before that I will have to.
So these two null spaces would be related by that lambda, right?
Which null spaces?
This is one null space n and the other is
The yes, this is there. Yeah, lambda will be will appear here. Yes,
n equal to lambda and tilde.
not that directly, not that directly. Yes, because you know this is just sum of two matrices. So, it is not necessarily true that the null space this and this n tilde are related by through just by lambda. Okay.
But if I understand correctly, these two are related by these two equations are just like this lambda omega.
Yeah, that is true. That is true.
When you take like
Yeah. So basically this means, you know,
so if you write lambda gamma plus iota omega by 2 lambda, then that gives the other one. But
yeah.
if you
So
take lambda
in principle, yes. So in principle, there can be overlap between this n and n tilde. Okay, there can be overlap, and there can be situations where there is no overlap. No overlap means, you know, these are subspaces. You can show that these are subspaces. So then it's a trivial overlap. Namely, the null vector is the only common vector between n and n tilde. That can also happen.
lambda can be adjusted.
Yes. Of course. Yes.
Some overlap or no.
Yeah. Exactly. Okay. So yeah, one more thing that I would like to introduce here. So you see that this is of course a subspace, right, of C to n. Similarly, n tilde, because null spaces are subspaces, right. Okay. Okay. So let me introduce a real part of n. So this is basically subspace of the 2n dimensional. So here n is a n plus m, right, okay, small n plus small m, 2n dimensional phase space, which I am calling as P, consisting of all the, or you can say that, yeah, span by, consisting of or span by, whatever you want to call, all the real parts of the elements of the vectors in n. So, do you follow that? So, basically if I look at n, this is a complex vector. So, it will have real and imaginary parts. So, so the real part of each vector is a 2n dimensional vector, which is an element of this phase space, right. Okay. And I take the linear span, real linear span of course, of all those real parts. Is that okay? So, this is a complex vector. So, I can write phi as phi real plus iota phi imaginary, right. So, so this is 2n dimensional real vector, this is also 2n dimensional real vector. I only consider this part. So, that will span this real of n. Similarly, I can define real of n tilde, all the real parts of the vectors. Okay. So, what one can prove is that an n mode Gaussian state rho is pure. So, it is a pure Gaussian state if and only if this real part of n is equal to my entire phase space. No, yes, it is the entire phase space. Okay. So, I mean there are other versions of this result, but anyway we'll get back to it later. Okay. So, I am not going to prove it now, but I mean one can also prove in a different way. Let me put it in a different way, so that things will become easier. Yes. So, for example, let me erase this part. Okay. So, let us say I take rho as a Gaussian state. I am not specifying what is its how many modes it has, right. Then, so rho is pure. So, this means that rho square is equal to rho, right. In fact, you can also prove that trace of rho square is equal to 1, right, because for no other state this will happen. Okay. Sorry? Yeah, infinite dimension also. This is true. No, because if you take these, of course, trace has to exist, otherwise it does not make sense. Density matrix trace will always exist. Which one? No, yeah, I mean the thing is you will have, so any operator A, if you take trace, of course, it has to be trace class operator, otherwise it does not make sense, but density matrices are always trace class operators. So, rho square is also trace class. Okay. So, trace class means its trace is finite. Okay. Yes. How do you define square of a matrix?
Yeah, like they are infinite dimensions. So through integrations or.
Yeah. So, in this case it is much easier, because you have this Wigner representation or other things that you can do, but for generic case you cannot, because there will be problem of convergence and all that. But here it is not a problem, because rho is a bounded operator, even trace class operator, everything is, by definition you can take square of that. That is not a problem. Okay. Even for non-Gaussian states, this is just state, whether it is Gaussian or not, forget it. For a density matrix, all these properties are valid, whether it is finite dimension, infinite dimension, because this is a bounded operator, any density.
These are valid that I am how will you take a square of an object which is infinite dimensional? Like through a Wigner representation, that I understand. Like
yes.
From there you can do it.
Yeah. So, this you can take in some in some limiting sense. For example, you can take like you have two operators, let us say these are both trace class operators, and I am assuming that this A into B is also trace class, otherwise it is a problematic thing. So, how will you take the product of that? This is of course a bounded operator in infinite dimension also. So, then you can define its product. How do you define it? Simple thing, you take j and k, and then this should be what? This should be basically sum over alpha a j alpha B alpha k, right. Okay. It is infinite dimensional, continuous means this is infinite dimensional. Now, the assumption is that this is a convergent sum for every j and k, otherwise it does not make sense. If you deal with bounded operators, trace class operator, this is natural.
Are there some cases of practical interest where this convergence is an issue?
Yeah, there can be, yes, of course. You know, this is the simple, I mean, this is the well known example. You know, generally in finite dimension, if I take commutator of this, okay, which is equal to C, say, then in finite dimension what do we do? This is basically, if I now take trace of this is equal to trace of this, right, and this trace is trace of AB minus trace of BA, and because trace is, you know, cyclic, so this will be 0. So, 0 is equal to trace of C, so which is fine, but now I take A is equal to your position observable and B is equal to momentum observable, then what you have is Q P is equal to iota h cut identity, right. So, now if I apply this formula trace of this, according to this will be 0 and this is infinity, right. So, this cannot be done, which is why, you know, this trace is, so you cannot apply the cyclic property here for infinite dimensional systems. Okay. So, now if I now try to figure out, so what is trace of rho square, which is 1, and this is, you know, basically, you know, if I take two density operators rho and rho prime, then in terms of Wigner distribution, so I am talking about this single mode case, but it can be generalized for multiple mode also. So, this is dx dp w rho x and p times w rho prime x and p. Okay. So, this is how you calculate for, this is for single mode, n mode case you will have to the power n or something like that. Okay. So, this will be therefore 1 upon 2 pi dx dp w rho x p square, okay, right. And so, once you assume that rho is Gaussian, so for Gaussian rho, what happens is w rho of x p, this is 1 by square root of determinant of this covariance matrix times exponential of minus half, this is x p, then gamma inverse x p, right. I am talking about the single mode, but this can be generalized for multi-mode case. So, this is the Wigner function. So, if I do that here, so what you will have is 1 upon 2 pi dx dp, then here it is 2 pi determinant of gamma, then exponential of, this is minus x p gamma inverse x p. Okay. So, now if I take this gamma, because this is positive definite matrix. So, let us say this is S transpose some diagonal. So, diagonal gamma 1 gamma 2 S. So, S is an element of SO2, because I mean this I can diagonalize by that, and this gamma 1 gamma 2 of course we know that these are positive, okay, because this is a positive definite matrix. So, what you will have is so now you take this S x p as your x prime p prime. So, this is a rotated frame. So, this will be 1 by twice pi determinant of gamma t x prime, because of rotation the Jacobian of the transformation is 1, and this will be exponential of minus 1 by gamma 1 x square minus 1 by gamma 2 p square, right, okay, because then it will become diagonal, right. So, now this is, so I can now split it, and this determinant of gamma is basically gamma 1 into gamma 2. So, this is 1 by twice pi gamma 1 gamma 2 into, now this is you can have just Gaussian integral product of these two Gaussian integrals. So, this is it's like this e to the power minus alpha x square dx minus infinity to plus infinity, right, and this is what, this is alpha is positive number. So, this is pi by alpha, right. So, this will be yeah. So, this will be, here it is pi gamma 1. So, this is pi square gamma 1 gamma 2. So, which will be 1 by 2 square root of determinant of gamma, something like that, okay, right. So, you see that therefore, determinant of gamma is equal to 1 by 4, and this we know that for coherent states, for example, single mode coherent state, this is what you will have, because for coherent state this gamma is, so if rho is this projection on this single mode coherent state, then we know that gamma of rho is equal to half identity 2 plus 2 for this single mode case, right. So, therefore, its determinant is 1 by 4, right. So, so what you see here is that purity of this Gaussian state implies, so yeah, I think what you will have that n mode Gaussian state is pure. It will imply that determinant of this gamma, this should be equal to, so for this is 2, I think it should be 2 to the power 2 n, something like that, okay, something of this form it has to be. Anyway, so there are different versions of this purity of Gaussian state. One is that, there are other ways also. So, anyway, so we will use some of them. Okay. Okay.
Trace rho square equal to 1 is necessary and sufficient for Gaussian.
Trace of rho square is equal to 1. Yeah.
It's necessary and sufficient.
Yes. Trace of rho square is equal to 1.
For pure Gaussian.
I mean, trace of rho square is equal to 1 for purity, whether it is Gaussian state or not, it does not matter. Okay. In fact, there is this famous theorem called Hudson's theorem, which tells that if Wigner function of a pure state is positive, then it has to be Gaussian. So, if I give you a pure state whose Wigner function is positive, positive means positive semi happening, that means it is a probability distribution, then it has to be Gaussian.
That's called Hartson's theorem.
Hartson's theorem, yes, yes.
So when was it published?
Yeah, maybe some mathematics journal, I do not know. I think this is in 74 or somewhere, something like that. And then people try to, so this was for single mode, then it was generalized for multi mode, and then people try to extend it for mixed states case. Mixed state case, it is not always true, under certain condition it will be true. Okay, good. So, now yeah. So, again I take n plus m mode state rho a b, whether it is Gaussian or not, that will come later. Okay. So, this I say that this n modes corresponds to A subsystem and this corresponds to B subsystem. Okay. Maybe it is with Alice and Bob. Okay. So, here if I look at the phase space, which I have called P or P A B if you want to call. So, this is your P of A direct sum P of B. Do you agree with me? Because when you have the vectors corresponding to A subsystem, phase space vectors, and then the components corresponding to B subsystem, right. And if I look at the symplectic matrix omega, this will be basically omega A, omega B, right. Why? Because you know what is omega? Omega is omega, let us say alpha beta. This is what? This is your R alpha, R beta, right, maybe iota this thing. Okay. So, this is how you will have, not iota, no, iota is not, is that correct? Let us say that is correct, yes. Yes. So, this is your thing. So, therefore, you know if you group it like A and B, then this is what you will have, right, and it will have all these properties. Okay. So, if I look at this rho A B going to rho A B partial transposition with respect to A subsystem. So, this will correspond to basically, so this will provide omega going to omega tilde, which is lambda omega lambda, and this should be, if you calculate carefully, it will be minus of omega A plus omega B. I think so, you know, this is how we will have. So, remember this lambda is your this diagonal matrix, right, on A subsystem only 1 minus 1, then 1 minus 1, 1 minus 1. This is for 2n modes, and then 1 1 1 1 1 1, and this is for 2m modes. Okay. So, this is how it will work. Instead of A, if you would have chosen B, then it should be replaced by minus omega B. Okay. Right. Is that clear? Okay. So, now let us take now let us take product state rho A B is equal to rho A tensor product rho B. So, this is a product state. Okay. Let us take that. Okay. So, then what will be these gamma rho A B? Let us say it is j kth entry. So, this will be trace of half, well this is basically rho A tensor product rho B times half, this is the anti-commutator of R j R k, and then minus R j, this is rho A tensor product rho B times R k rho A tensor product rho B. Okay. So, this is what you will have. J and k, J and k runs from 1, 2, 3 up to 2n plus 2m. Okay. Now, depending upon whether j belongs to 1 to 2n and k belongs to 1 2n plus 1 to 2n plus 2m, something like that, all these classifications you can have, it is not difficult. What you will figure out that this is nothing but gamma of rho A direct sum gamma of rho B. Okay. So, for any product state, of course, this has to be, so what I am saying is rho A tensor product rho B. So, this is what you will have. Okay. So, you can prove from here that depending upon the choice of your j and k, this is what ultimately you will have, right. Clear? Okay, good. So, this you can prove. Okay, fine. And now, if so assume that for a 2n plus, or let us say n plus m mode Gaussian state rho A B, we have gamma of rho A B is equal to gamma of A plus gamma of B. I am not saying that this is reduced density matrix of A B and this is corresponding to reduced density matrix. This is how you write the covariance matrix, one for A subsystem, one for B subsystem. Okay. This is the covariance matrix for this Gaussian state. Then you can prove that this Wigner function. So, this will imply, this is straightforward to prove, that Wigner function of rho A B at R T. So, this R is an element of R to the power 2n plus 2m, right. because this is my phase space. So, this I am writing here transpose because R is a column vector. So, this is a row vector. So, this you can prove that this is nothing but W rho A at R A transpose times W rho B R B transpose, where your this R is equal to R A plus R B. As usual, this is in that sense you split it into the A and B parts, this your phase space. This is an element of P of A, phase space for part A, and element of P of B. And what are these rho A, rho B? Rho A is equal to trace over B of rho A B, and rho B is equal to trace over A of rho A B. So, indeed, so this gamma A corresponds to gamma of rho A, this gamma B corresponds to gamma of rho B. Okay. So, therefore, you see that if you have a Gaussian state of n plus m mode, then its Wigner function, in fact, this is both way true, it is not just one way, this is both way true. So, its Wigner function for, if you can split it in this form, then its covariance matrix will be of this form, and if the covariance matrix is of this form, you can split this thing in this way. And in fact, this implies that basically your rho A B is equal to rho A tensor product rho B. Okay. No other solution is there, because we have seen that for product state this is the form. Opposite is also true. Yes. Yes. Which one?
That if my covariance matrix is of that form, the state will be separable. So that is
State is a product state. Yes.
state
Yes.
is a product. So that
Yes.
is true from the first argument, right?
No, this is only for the Gaussian state, not for general one. Non-Gaussian state I cannot say this thing. The entire statement is not true for non-Gaussian state. For Gaussian state, entire statement is true, and one way of course is true for any state.
For any state, if it is product, then
Then it is of this form,
But if it is of this form, then it is not true.
not necessarily of this form.
For any gen, for Gaussian, it is true.
Gaussian it is true. Yes.
So, is that some kind of separability criterion?
Not exactly. Not exactly. Yeah. So let me come back to that for separable one. Let us say I take rho A B, this is n plus m mode state, and let us assume that this is separable. Okay. Then I can have rho A B is equal to sum over, let us say, alpha lambda alpha, let us say this is psi alpha for A subsystem, tensor product phi alpha for B subsystem, and this is a probability distribution. Right? This I can always write, because this is a separable state. Okay?
But then the product state is already in this form, right?
Yes, yes, product state is already in that form. Yes. So then, if I want to write down rho gamma A B, if you look at the definition of the jkth entry of this covariance matrix, you will figure out that this is nothing but sum over alpha lambda alpha covariance matrix of psi alpha A tensor product phi alpha B. Do you agree with that? I mean, this is the way we have defined here, this is a linear process, this trace. So, this is how it will have. And now, this is sum over alpha lambda alpha gamma of psi alpha for A subsystem, direct sum gamma of phi alpha for B subsystem, right, according to our this result, okay, because it is a product state. Okay. Yes. And so, you see that for a separable state, and you have basically this kind of decomposition of the covariance matrix, right. And in fact, if you look at it carefully, you see that the rho of A, so which is the covariance matrix of the reduced state. So, this is nothing but sum over alpha lambda alpha covariance matrix of psi alpha A, and similarly rho B is equal to sum over alpha lambda alpha covariance matrix phi alpha. This is on B, right. This is how you will get. Okay. Now, these are matrices. So, this is a 2n by 2n real symmetric positive definite matrix, right. Similarly, this one is 2m by 2m real symmetric positive definite matrix. Okay. So, when I write this thing in matrix form, how will this lambda work here? Just yes. So, lambda will basically will multiply all the matrix elements of this, similarly all the matrix elements of this, right. Yes. Yes, exactly. So, therefore, I can write it as, so this is what I want to tell. So, can I write it as gamma of rho A plus gamma of rho B? Is that true? That is true, right. Okay. So, you see that for separable state, the covariance matrix is also of this form, not just the product state. Okay. Right. And this will help us to understand the separability and positive partial transposition, etc. Okay, good. What is the time now? Let me see how far I can go.
Linear function then for even separable states is like this.
Is that the case for product state?
Gaussian. So for Gaussian separable.
No, let me see. So your rho AB is sum over alpha lambda alpha psi alpha A tensor product phi alpha phi. This is for any separable state, right? So, if I now look at the Wigner function, so Wigner function definition is yes. So, basically it will be sum over alpha lambda alpha Wigner function of psi alpha A tensor product phi alpha B. Is that correct? Because you see the way we defined Wigner function is this thing, Wigner function of rho, let us say R. So, this is integral, so this R E belongs to this 2n plus 2m whatever you want to call d of R. Yeah, here it is x1 minus x1 prime so how many so this is xn, let me call it as 2n, okay, so make my life easier, xn minus xn prime, then rho, then x1 plus x1 prime, xn plus xn prime multiplied by exponential of iota x1 prime p1 xn prime pn. So, this is my Wigner function, right. So, if I take convex combination of these, basically it will be again convex combination of this thing. Okay. So, therefore, this is the form. And now, Wigner function wise what happens? It is so, this is psi alpha A and this should be now R A, right, into phi alpha B, this is R B. So, this is my Wigner function at R. Okay. Yeah, so yeah, this is how we will have. So, it will not be product, I mean in the sense that this is not in general equal to Wigner function of sum over alpha lambda alpha psi alpha A, this is on R A times Wigner function of alpha lambda alpha phi alpha B, this is R B transpose. No, it is not like that, okay, because yeah, because if you do this thing, it will be basically this part if you do this thing, but if you do this thing, then you will have also product of this lambda alphas, right. So, therefore,
Sum over lambda square is also 1. Just like
yeah, that
it
can
becomes
yes, that is generally not the case.
that's
That is where that happens only when you have only one term,
1 and 0s.
everything else is 0. Yes.
Everything else is 0.
Yes.
But if the state is Gaussian, then this will imply that, right?
Which will imply that
This equation, the Wigner function will be still with this because this is for general.
yes,
But if the state is Gaussian,
yes,
right, then will this condition imply that basically will the same theorem will hold even for separable states?
So for separable states, we wrote the what we were writing there, that if gamma is the sum of individual gammas, then Wigner functions become the product.
yeah. What did I say about Gaussian states here?
So that's true for Gaussian states. That
Yes.
if gamma is sum over individual gammas, then Wigner product is the product. Wigner function is the product over individual.
Right.
But we established here that even for separable states, this is true.
Yeah, that is true, but
So the first condition holds, so the second condition is not true.
No. So the second, so that condition on the covariance matrix.
yeah, that is the so whether it is separable or product state, this is true
Yes,
Yeah.
exactly.
at the level of covariance matrix.
And this
But
is also true.
this is true for any separable state.
Exactly.
This one.
Yes.
This is true for any separable state.
So if that is true, this will be true because that is a general condition,
Yeah.
right? But for Gaussian state, does the opposite also hold? That Wigner function is this, then that will be this.
If the Wigner function is a product one, that's what, right?
Yeah, this of this form.
Yeah,
So,
yeah,
so
right,
this
right.
theorem is for Gaussian states. The
This is
reverse
for Gaussian
only,
state,
Reverse
yes.
is only true for Gaussian states.
I think so. Now let me think about it. Whether separable for separable Gaussian state, no, not. I don't think you can write in this form. Maybe I have exaggerated this thing. So basically, this is also one way true. Otherwise, it will be a problematic thing. See, even for separable Gaussian state, I cannot write the Wigner function of this state as a product of individual, reduced density matrix Wigner functions. I cannot write that. I can only do that if it is a product state. Okay, so, but this is true. This is true in the sense that if I know that this is a product Gaussian state, of course, this is true. Otherwise, you cannot carry forward there.
Opposite is also true, right? For product Gaussian state.
Product Gaussian state, of course, this is true.
That if my Wigner function is a product, then that is.
Yes, yes.
If you have a separable Wigner states, then that is your Wigner function. It is not a product.
No, it is not a product.
It's like a sum of products, right?
Yeah, sum of
Sum of
products.
products. So for Gaussian states of this form, will it also imply that if my Wigner function is of this form, then my covariance matrix will be just a direct sum of the reduced parts?
Tell me again, what?
So if for Gaussian separable states, if my Wigner function is of this form,
Yes.
is it true that the covariance matrix will be?
You are saying for a separable Gaussian state.
Yes.
Yeah, if you know it is a separable Gaussian state, why do you go through this Wigner function to figure out the covariance matrix? Because covariance matrix, I said that for a separable state, whether it is Gaussian or not, this is the property of the covariance matrix, right? If this is separable, then gamma rho AB is equal to this.
Then what is the meaning of this theorem?
No, this I have done just only for product Gaussian state,
Yeah. So
which is of course is true from here also, you see.
exactly. That's what I was. Because if you know your Gaussian state is product, then by definition you know that it's this
Yes.
covariance matrix.
That is a special case of this.
Yes.
And we know that if your two mode, this AB, rho AB is Gaussian, then individual subsystems are also Gaussian. So therefore, this one is a Gaussian state, this one is also a Gaussian state.
So then,
But you cannot write it in this form.
yeah, that makes sense. So we write it there. So let me ask a restrictive question. So if I know my state is Gaussian,
Yes.
that's it. Then you give me its Wigner function. It's of this product form.
It is of this product form. Yes.
Does it imply that my state is product?
Does it imply that my state is product? Okay. Yes, it is.
It implies.
It is.
So similar question. If I tell you that the state is Gaussian,
Yes.
and then I give you Wigner function of this form.
Which form? This form.
Yeah.
Yes.
Does it imply that my state is separable?
How do I know that? Because when you write in this form, if you explicitly provide this form,
Yeah.
then of course from here I can figure out the Wigner function of the reduced states,
Yes.
right? So then from there I can figure out whether the reduced states are also Gaussian. That I can figure out. But to say that this is separable or not, it is a bit tricky. This I cannot
So
tell
that
directly.
thing won't hold here.
Yes, that I cannot say directly. Okay, yeah. So for Gaussian states, some of the things we can do, but not everything. Okay, so this I'll tell you now. Okay, so what are the things that we can do for Gaussian states?
necessary condition for separability.
This is a necessary condition for separability. This is also a necessary condition for separability.
Which,
This one, that gamma a rho a b is this thing.
oh, so not all states of this form are separable.
Yeah, of course. So here is this result which they call as proposition. I don't know why they call it as proposition 1, but let us say is a from mathematician's perspective. Okay. So it has two parts. This part 1, it tells you that gamma rho a b be the covariance matrix of an n plus m mode. So, whenever I write n plus m, n corresponds to a subsystem, m corresponds to b subsystem. On mode separable state. Rho a b having finite second moment in. So, you know what does it mean? It means that the entries of these are finite. Okay, entries of this gammas are finite because this is finite second moment. Okay. Then there are covariance matrices gamma a. When I write gamma a, it means corresponds to the a subsystem, and gamma b, this means corresponding to the b subsystem, such that this gamma rho a b is greater than or equal to gamma a plus gamma b, and this means what? This is basically gamma a 0 0 gamma b. So, once again, if this is a separable state having finite second moment means all the entries are finite of this covariance matrix. Then you can figure out covariance matrices for a subsystem and b subsystem. These are not necessarily covariance matrices of the reduced states rho a and rho b, not necessarily, but you can figure out them such that this is the case. Okay. Now, okay. So, the part 2 is, which is basically the converse of this. It tells you that, so let me call these as condition 1. If condition 1 is satisfied by the covariance matrix gamma rho a b of an n plus m mode Gaussian state, rho a b, then it is separable. So, you see this is somewhat similar to what we have done in Simon's work, 1 plus 1 dimensional case. So, in Simon's work this is true, I mean this was kind of true. So, this tells you that if rho a b is separable, then this condition has to be satisfied. You can figure out such gamma a and gamma b covariance matrices. The converse is also true. So, if this condition is satisfied, then, and if you know that the state is a Gaussian state, then you can prove that this is separable. Not for generic state you can prove, but if it is known to be Gaussian, then you can prove that this is separable. Okay. Is that clear?
How to find these gamma L and gamma B?
Sorry, what?
How to find these gamma L and gamma B?
Yeah. So that this method tells you that there exists such gamma A and gamma B.
That this will.
That so that this condition will be satisfied.
But these are not covariance matrix of the individual subsystem.
No, not
There are
necessarily.
some,
These are valid covariance matrices
but some
for the subsystems A and B, but not necessarily covariance matrices of subsystems A and B. I mean reduced states of A and B. Okay. Yeah. So this is basically.
So it's condition one in some sense saying that like because we already know that gamma of rho AB is gamma rho A, there is some gamma rho B. We proved that earlier.
Yes, if it is separable.
Yeah, if it's separable, which is there, not there.
Yeah. So therefore, you can figure out that.
So then gamma rho A is greater than gamma A and gamma rho B is greater than gamma B. So is that kind of saying that gamma rho A and gamma rho B don't saturate the uncertainty condition? Is that
No,
what
they
you're
satisfy because they are covariance matrices. They will satisfy.
satisfy, but they don't saturate in the sense that the equality doesn't hold, just the
Yes.
it is strictly unequal. Something.
Kind of. You know, this inequality sign doesn't mean that they cannot be same. I mean,
Okay.
they can be same also. Yeah. Okay. So, so maybe I'll just write down the results first, and then I'll give the proof of this, because the proofs are bit lengthy. So, I'll just give the proof of this later. Just a minute. Yes. So, this is for proposition 1. Okay. So, I will give proof of this maybe in the next class, but yeah, this in fact these proofs are bit involved proof. Okay. Not the first one, but the second one. Second one is bit involved proof. Okay. Okay. So, then proposition 2. So, I am writing down the main results, and then we will have to, when I give the proof, we will try to motivate. Okay. Again it has two parts. Part 1, right. So, this gamma rho A B be the covariance matrix of an n plus m mode state rho A B having finite moments. I mean, you can say second moment, but more generally it is finite moments. Okay. Second moment finite is fine, but you can have more generally, all the moments are finite. All the moments being infinite are not physical.
But some, like say, third moments are infinite, so these are physical states.
In general, not. Infinite moment states you should not consider them. No. See, the thing is that if at least second order moments are not finite, then this is not a finite matrix, right?
It's
Okay.
not a state.
I cannot say it is not a state. You see, there can be some non-Gaussian state for which second order moment is finite. This is okay. But because if it is a non-Gaussian state, all the higher order moments are non-zero.
Yes.
Okay, some of them can be finite, some of them can be infinite also.
like, so these moments are basically some expectation values,
Yes,
right? Expectation values and correlations.
yes, yes,
So if some of them are infinite, right, it means that expectation value is blowing up
yes,
or correlation is blowing up.
yes.
So like, how will that kind of scenario be physical?
Yeah, it can happen. Of course, you will. It is unphysical in the sense that let's say I take squeezing for example. So if you take infinite squeezing, there can be something which which are generally unphysical. Okay. If you take for example non-Gaussianity like photon addition one after another, if you do, then of course at some point of time you will have infinite moments. Okay. So, there should be always this energy restriction, but these are mathematical results. So, they do not care about whether you are talking about such energy restrictions or not. So, this will of course put such kind of restrictions, these finite moments. Okay.
Or even if you have some kind of a uniform probability distribution in a very large system,
Yes.
that is also something with the divergent mean.
Exactly, exactly. Yes. So, yes, for realistic system you cannot have these infinite moments and all that. Yes. But these are just mathematical results. So, for them it does not matter what particular physical restrictions are there. Okay. And let this gamma rho A B T A, this is greater than or equal to 0. So, you are taking, so there it was separable state, now I am taking PPT state. Separable state can also be, it will be PPT, but this is more general. Then gamma rho A B plus iota by 2 minus lambda A plus lambda B greater than or equal to 0, where this is equal to lambda omega lambda is equal to minus plus B, right. This is what we have seen. Now, this we have already mentioned that this has to be the case, because this is positive partial transposition. Part 2, if gamma rho A B plus iota by 2, this is minus omega plus omega B greater than or equal to 0 for an n plus m mode Gaussian state. So, this theorem you will see, it is basically a kind of generalization of what I have written there, Gaussian state rho A B, then rho A B T A greater than or equal to 0. Okay. So, here it was separable, now it is PPT. So, it is a kind of generalization of that. Okay. Again this is so this is very simple, but this part is involved, right. Okay. So, I will not again prove this thing, not now, I will give the proof, and finally, this is what they have proved, that let me look at it, just a minute. Okay. So, there is another result which is proposition 3. So, this says that gamma be a PPT covariance matrix. What does it mean? Gamma is a PPT covariance matrix. It means that gamma is a So, gamma is a real symmetric positive definite matrix such that gamma plus iota by 2 this is greater than equal to 0 and gamma plus iota by 2 tilde is greater than equal to 0. So, this is my PPT covariance matrix. Okay. So, basically it has to be covariance matrix of a state and also it has positive partial transposition, that is what it means. State is PPT, yes, it is a PPT covariance matrix.
When you define a PPT as a concept for the covariance matrix alone as a matrix.
You can, but that does not make sense. You will have to.
So this PPT means of the state.
Of the state, yes. Yes. So then gamma is minimal PPT. This minimal PPT means that is gamma is PPT covariance and for any covariance matrix gamma prime less than equal to gamma, we must have gamma prime is equal to gamma. So, it means that there can be no other covariance matrix gamma prime which is less than gamma, it has to be equal to gamma. So, this means it is minimal PPT. Okay. So, then gamma is minimal PPT if and only if a real part of n, you remember this is the subspace of the null space of gamma plus this iota by 2 omega, which is spanned by the real parts of this union real part of n tilde. So, this spans your phase space P, this is your entire phase space. Okay. So, this is what you will have. So, if it is a minimal PPT, so gamma is a minimal PPT if and only if this happens. Okay. So, with these three results one can then prove that if I take a Gaussian state 1 cross n mode, then rho a b T a greater than equal to 0 implies and implied by rho a b is separable. So, using all these three propositions one can prove this result. Okay. That for 1 cross n mode or n cross 1 mode Gaussian state, PPT means it is separable and vice versa. There are no bound entangled states for this system, and then one can construct bound entangled states for let us say 2 cross 2 system and higher system. Okay. So, that is basically the result. Okay. So, I think I am too late today. So, maybe next class I will discuss about this proof. Maybe I will not go through all the proofs, but at least some of them.